Okay, so let me see. This is the sheet that we did before, and we stopped at 30. And I can just go to that line. You'll see that we stopped at an angle of 30 degrees. We interpolate it down. Now we want to take this out to 15. If we go back to our sheet here, you'll see at 15 degrees, we are at 0.1890 meters. So at 45 degrees, I said 15 degrees, that's a mistake. But at 45 degrees, we have a height of 0.1890 meters. So let me go back here and let's just go ahead and grab a few of these cells. We're gonna drag this down 15 slots. It's 44 right there. So we need one more, that's 45. Let's go ahead and drag down our velocity here. And of course, the conversion from angles to radians is just a calculation, so we're doing the same thing that we did before. I know I'm going fast, but my expectation is that you all have a very good grasp of this right now. So of course, I'm not trying to be as pedantic as I was before. So here we have 45 degrees. I'm going to go ahead and put in that value, 0.1890. Okay. And we're going to increment in between those two values. So I'm going to say equal to, grab a grouping symbol and go down here. And then subtract the previous location's height. And then we want to divide this by 15. So this is going from 30 to 45, that's 15 degrees. So we're incrementing in units of 1. So, and I know you guys know that already, but still, for some reason, I felt like I needed to say that. So I'm going to assign this cell the same value as the one above it. And then I'm going to fill and drag this one down. And it's going to stop at 44, an angle of 44. So now let's go ahead and interpolate our height here. And just in case you don't know what I'm saying when I say interpolate, we're just making a guess. It's like we're making an assumption that every time this angle increases by 1 degree, the actual height is going to change by 2.5 millimeters. Is it true? Can we do it a different way? Of course, all of that stuff. So let's just drag this down. And you'll see that you have 0.1865, and then we have 0.189. So the idea is that you do not want to go above 0.189. Okay, if your interpolated heights went above that, then something would be wrong with your calculation. So let's go ahead and do our calculation for the time of flight. Just drag that down. And let's do our angles. And then our predicted range. Okay. So again, we don't have a range measurement, and thus we don't have a percent error. But we do want to correct for our graph here. So right now we're just going out to 30, as you can see. Let me see if I click right here. You can see that we're only going out to 30. So we want to go ahead and extend that to 45. You'll see that our data set stops at 30. Let's just go ahead and grab one of those handles and drag down to 45. And you'll see the correction on the graph. So you can see the graph is being corrected even more and more. So what the graph is going to allow you to do is to make a better hypothesis. You know, it's no need to get into, well, this is absolutely truth and all of this, but you could say, well, this is a very good hypothesis, all right? We're in a controlled environment, so you would not necessarily be able to utilize this if wind is blowing. If you take it outside and the wind is blowing and water is coming down, or if it's raining, this hypothesis, or to be able to draw a hypothesis from this graph would be a bit more challenging. It's not saying that you can't, but it would be a bit more challenging. It should follow along this one. All right, and you should be able to turn this in. I think that's all I'm asking you to do on this one. Cool beans?